What if I told you that somewhere in the dust-covered archives of our oldest civilizations lies a warning we never understood, a message carved in clay 5,000 years ago, describing an event that wouldn't happen for generations? What if the ancients knew something was coming and tried to tell us? This is the story of the last great impact, not the one that killed the dinosaurs, not a theoretical future catastrophe, but a real event, witnessed by real people, that may have been predicted by the most advanced civilization of the ancient world, the Sumerians, the first to write, the first to build cities, the first to study the heavens with mathematical precision, and perhaps the first to see what was written in the stars. But here's what keeps scientists awake at night. What if they recorded it before it happened? Our story begins not in ancient Mesopotamia, but in a climate-controlled room at the British Museum in 2008. Dr. Alan Bond, a planetary scientist with no background in archaeology, was doing something unusual. He was reading 5,000-year-old Sumerian astronomical records backwards. Bond wasn't looking for historical data. He was searching for something specific: a tablet known as the planisphere, a clay document recovered from the underground library of Nineveh, part of the ancient Assyrian Empire. But its origins were far older. It was a copy of an original Sumerian text, dated to approximately 3123 BCE. The planisphere is unlike any other artifact from the ancient world. It's a circular star map, divided into 8 sections, covered with constellation markers and numerical notations. For over 150 years since its recovery, scholars assumed it was simply an observational record, the ancient Sumerians cataloging the night sky. But Bond saw something different. He saw trajectory calculations, flight paths, impact predictions. Using modern astronomy software, Bond recreated the exact night sky as it would have appeared over Sumer on June 29th, 3123 BCE at approximately 4 a.m. What he found sent shockwaves through the scientific community. The planisphere wasn't recording the stars. It was recording something moving through them, an object on a collision course with Earth. And according to the calculations preserved in clay, the Sumerians saw it coming. 800 miles northwest of ancient Sumer, in what is now the Austrian Alps, lies one of geology's most puzzling mysteries: the Kofels impact structure, a massive landslide scar nearly 3 miles wide, with debris fields stretching for miles down the valley. For decades, geologists classified Kofels as the result of a natural landslide, a mountain collapse, perhaps triggered by an earthquake or glacier melt. But there was always something wrong with that explanation. The rocks weren't right. Minerals at Kofels show signs of extreme heat exposure, temperatures exceeding 1,200 degrees Celsius, the kind of heat that doesn't come from landslides, the kind of heat that comes from atmospheric entry. There's also the complete absence of a crater. If an asteroid struck here directly, there should be an impact basin. Instead, there's a pattern consistent with something else entirely: an airburst. Imagine an object roughly 300 feet in diameter, composed of ice and rock, entering Earth's atmosphere at 45 degrees. It's traveling at approximately 30,000 miles per hour, 40 times the speed of sound. At this velocity, atmospheric compression heats the object to plasma temperatures. As it descends through increasingly dense atmosphere, the pressure becomes catastrophic. At about 20 miles altitude, the object reaches its breaking point, and then detonation. The energy released would have been equivalent to a 1,000 megaton nuclear weapon. For comparison, the largest nuclear device ever tested, the Tsar Bomba, was 50 megatons. This was 20 times more powerful. The shockwave alone would have flattened forests for 100 miles. The heat pulse would have ignited everything flammable within visual range, and the acoustic boom would have been heard across continental Europe. But here's the truly remarkable part. According to Bond's interpretation of the planisphere, the Sumerians not only recorded this event, they calculated its trajectory before impact. They predicted where it would strike. To understand how this might be possible, we need to understand who the Sumerians really were. This wasn't a primitive civilization scratching survival from the desert. This was the world's first true superpower, with a level of astronomical knowledge that wouldn't be matched for thousands of years. The Sumerian priest astronomers were the NASA scientists of their age. They tracked planetary movements with obsessive precision. They calculated the lunar cycle to within decimal points of modern measurements. They identified all 5 visible planets and tracked their retrograde motions. They even divided the circle into 360 degrees, a system we still use today. But their greatest achievement was pattern recognition. The Sumerians didn't just observe the sky, they memorized it. Every star, every constellation, every planetary position was cataloged and cross-referenced across generations. They knew when something didn't belong. So imagine you're a Sumerian astronomer in the year 3125 BCE. You've spent your entire life studying the movements of the heavens, just as your father did, and his father before him. You know every star's position, every planet's cycle. And then one night, you see something new. A faint point of light where no star should be. At first, barely visible. But night after night, it grows brighter. And more importantly, it's moving. Not like a planet with its stately wandering, but with purpose, with acceleration, coming closer. You begin calculations. Using the mathematics passed down through your order, you plot its course. You calculate velocities, trajectories, intersection points. And slowly, terrifyingly, you realize what you're seeing. This is no wandering star. This is something that will touch the Earth. The question that has haunted researchers ever since Bond's discovery is this: how long did they watch it? How many nights passed between first observation and impact? Days? Weeks? Months? We may never know for certain, but if the calculations preserved on the planisphere are accurate, and Bond's reconstruction suggests they are, the Sumerians had at least several weeks of warning, long enough to calculate, long enough to record, perhaps even long enough to evacuate. June 29th, 3123 BCE, summer solstice season in Mesopotamia. The date encoded in the planisphere through constellation positions, a moment frozen in time and clay. For most of Sumer's population, this would have been a day like any other. The wheat harvest was underway. Trade caravans were arriving from the mountains to the north. Children played in the narrow streets between mud brick houses. Life continued as it had for generations. But on the great ziggurat of Ur, the astronomer priests knew different. They had been watching the approaching object for weeks now. What began as a barely visible point of light had become clearly visible to the naked eye. It no longer looked like a star. It looked like what it was, a harboring of doom, growing brighter each night. The object was now approximately 2 million miles from Earth, 8 times the distance to our moon. At its current velocity, it would reach atmospheric interface in less than 20 hours. The astronomer priests had made their final calculations. They knew, within a few hundred miles, where it would strike. And so, they did what their civilization had always done in the face of momentous events. They created a permanent record. They baked their observations into clay, ensuring that whatever happened next, the knowledge would survive. The planisphere was their testimony, a message to the future about what was coming from the sky. But did they warn others? Did they attempt evacuations? Did they understand the full scale of what was about to happen? Some researchers believe they must have. The Sumerian civilization had extensive trade networks reaching from Egypt to the Indus Valley. They had the fastest communication system in the ancient world, relay runners and riverboats that could carry messages hundreds of miles in days. If they knew destruction was coming, they could have spread the word. But would anyone have believed them? How do you convince people that fire is about to fall from heaven? That a star is going to strike the earth with more force than anything in living memory? The archaeological record gives us no clear answers. There are no mass evacuation sites, no clear evidence of population movements in the years around 3123 BCE. If warnings were issued, they either weren't heeded or weren't necessary, because the impact site was far enough away that most of Sumer would survive the initial blast. But survival comes in degrees, and what was about to happen would change everything. At approximately 4:17 a.m. local time, it begins. 800 miles to the northwest, over the peaks of what will one day be called the Austrian Alps, the object makes its final approach. It's traveling at roughly 30,000 miles per hour, Mach 40. At this speed, air cannot get out of the way fast enough. It compresses ahead of the object, heating to plasma temperatures. The asteroid begins to glow, then to burn. A streak of light across the European sky, brighter than any shooting star, brighter than the full moon. Across Europe, people wake to an unnatural dawn. In the British Isles, Neolithic farmers stumble from their huts to see the entire southern sky ablaze with light. In Scandinavia, hunters watch in frozen terror as day seems to break in the middle of the night. The light is bright enough to read by, bright enough to cast shadows. At 40 miles altitude, the asteroid begins to break apart. The thermal stress is too great, the atmospheric pressure too intense. Cracks appear in the cosmic ice and rock, widening into chasms. The single object becomes 5, then 10, then a shotgun blast of superheated fragments, all following the same trajectory. 20 miles up, the largest fragment, still nearly 200 feet in diameter, reaches its critical point. The atmospheric pressure exceeds the material strength of the object by orders of magnitude, and in an instant, it doesn't break apart. It vaporizes. The explosion releases energy equivalent to 1,000 megatons of TNT. To put that in perspective, the atomic bomb dropped on Hiroshima was 15 kilotons. This is roughly 67,000 Hiroshima bombs, detonating simultaneously in the atmosphere. The shock wave travels outward at several times the speed of sound. It reaches the ground in seconds, striking the mountain at Kofels with enough force to instantly superheat the rock face to 1,200 degrees Celsius. Stone doesn't melt. It vaporizes into mineral dust. The peak of the mountain, thousands of tons of solid rock, simply disappears. The remaining mass, destabilized and flash-heated, collapses downward in the largest landslide in European history. 11 cubic kilometers of rock, roughly the volume of 4.5 million Olympic swimming pools, cascades down the valley at 200 miles per hour. Everything in its path is obliterated, buried under hundreds of feet of debris. But the landslide is just the beginning. The thermal pulse from the explosion radiates outward at the speed of light. Every surface within visual range of the blast is exposed to heat equivalent to an industrial furnace. Wood ignites instantly. Vegetation flash combusts. In a radius extending for hundreds of miles, the forests of Central Europe become an inferno. Then comes the pressure wave. Trees that survive the heat are snapped like twigs, blown down in radial patterns pointing away from the epicenter. It's a pattern that will be seen again 3,100 years later at Tunguska in Siberia. Another airburst event, but only a fraction of this magnitude. 800 miles away, on the ziggurat of Ur, the astronomer priests see it first. The northern horizon, where no sunrise should appear for another 2 hours, suddenly blazes with light. Not the warm orange of dawn, but a harsh white brilliance that turns night to day in seconds. Across Mesopotamia, people wake to the impossible. The sun seems to be rising in the north, except it's not the sun. It's brighter, harsher, and tinged with colors that seem wrong. Red and orange and purple, flickering and pulsing. The light lasts for approximately 15 minutes, the duration of the initial explosion and the massive firestorm it triggers. Then slowly, gradually, it fades. But as it fades, something else becomes visible. The sky to the north is no longer black. It's brown, then gray, then a sickly yellow-green. A cloud is rising. Not a normal storm cloud, but something monstrous. A churning, roiling column of ash and debris reaching into the stratosphere. It's the combined output of vaporized rock, burning forests, and hundreds of cubic miles of pulverized mountainside being lofted into the atmosphere by convection currents hotter than a blast furnace. The plume rises to an altitude of 60,000 feet, twice the height of Mount Everest, where it encounters the jet stream. And then it begins to spread, drifting east and south, carried by high-altitude winds toward the Mediterranean, the Middle East, and inevitably toward Sumer. The astronomer priests understand what's coming. They've calculated the trajectories, predicted the impact point, recorded it all on clay. But they couldn't have predicted this. Nobody could have. The sheer scale of the atmospheric disturbance exceeds anything in their experience or their records. 6 hours after impact, the leading edge of the ash cloud reaches Mesopotamia. The sun, which has only been up for a few hours, begins to dim. Not like clouds passing overhead, but like something fundamental is changing. The light takes on a strange, diffuse quality. Colors become muted. Shadows disappear. The temperature, which has been rising toward the usual summer midday heat, suddenly plateaus, then begins to drop. Within an hour, it feels like evening. Within 2 hours, people are reaching for winter cloaks in the middle of summer. And then the ash begins to fall. Not like rain, but like snow. Fine gray particles, settling on rooftops, coating the streets, covering the fields. At first, it's a curiosity. Children try to catch it, examining the strange gray flakes that don't melt. But it doesn't stop. It falls all day, all night, all the next day. By the third day, there are several inches of ash covering everything. The river water is gray and gritty. Crops are dying under the weight. Animals are coughing, struggling to breathe. And still, the ash falls. The sun is now just a dim orange disk struggling through the haze, providing barely enough light to see by, no warmth at all. What the Sumerians were experiencing was the beginning of a volcanic winter, except caused not by a volcano, but by an impact event. Millions of tons of fine particulate matter suspended in the stratosphere, blocking sunlight, disrupting weather patterns, changing the climate across an entire hemisphere. The effects were immediate and catastrophic. With 30 to 40% less sunlight reaching the surface, temperatures dropped by as much as 5 degrees Celsius across the Middle East and Mediterranean. That might not sound like much, but when it happens in a matter of days, during what should be the growing season, it's devastating. Crops failed across the region. The wheat and barley that should have been ready for harvest simply stopped growing, then died. The complex irrigation systems that made Sumerian agriculture possible couldn't compensate for the sudden cold and the lack of sunlight. Animals, already stressed by the cold and the ash in their lungs, began to die in large numbers. And this continued not for weeks, but for months. The ash cloud, replenished by the massive firestorms still burning across Central Europe, persisted through the summer of 3123 BCE and into the fall. By the time the skies finally began to clear in late autumn, the damage was done. An entire growing season lost. Food stores depleted. Population stressed past the breaking point. The archaeological record from this period shows something remarkable: a sudden, sharp decrease in settlement sizes across Mesopotamia around 3100 BCE. Villages that had supported hundreds were abandoned or contracted to a handful of families. Trade goods become scarce. Luxury items disappear from the archaeological record entirely. And in some sites, we find mass graves. Unusual clusters of burials dating to this narrow window of time, suggesting disease outbreaks or starvation events. The kind of archaeological signature that appears during times of severe crisis. This is supported by climate proxies from ice cores and lake sediments. They show a brief but severe cooling event right around 3100 BCE. Exactly when the planisphere says the impact occurred. Exactly when the geological evidence from Kofels suggests catastrophic disruption. The timelines align. So the question becomes, did the Sumerians know? Not just that an object was approaching, but what it would do. Did they understand that they were recording not just an impact, but the end of an age? When Alan Bond first published his interpretation of the planisphere in 2008, the response from the scientific community was mixed. And that's putting it charitably. Bond's theory was bold, that an ancient civilization not only observed, but predicted a catastrophic impact event, recording it with sufficient accuracy that modern software could reconstruct both the observation and the impact. For many researchers, this was a bridge too far. The criticisms came from multiple directions. Archaeologists questioned whether the planisphere was even an astronomical document. suggesting it might be an administrative record, a mathematical exercise, or a religious diagram. Astronomers questioned whether the calculations Bond used were really present in the cuneiform script, or whether he was seeing patterns that matched his hypothesis. And geologists remained skeptical about Khufuls itself. Yes, there was evidence of extreme heat. Yes, the timing seemed to align with a cooling event in the climate record. But the complete absence of impact melt, shocked quartz, or other traditional markers of an impact event made many geologists uncomfortable with the asteroid hypothesis. The debate crystallized around a few key questions. First, was the planisphere actually recording an astronomical event? Or was Bond projecting modern knowledge onto an ancient artifact? Second, did an impact really occur at Khufuls around 3100 BCE? Or are we connecting unrelated geological and archaeological events? And third, even if both are true, is there any real connection between the Sumerian tablet and the Alpine impact? Bond's defenders pointed to the specificity of the alignments. When you input the exact date and location encoded in the tablet, the match between cuneiform markers and constellation positions is remarkably precise. Too precise, they argue, to be coincidental. The probability of random marks on a clay tablet aligning with actual stellar positions, planetary locations, and a moving object on a collision trajectory is astronomically small. For Khufuls, the evidence has actually grown stronger since Bond's initial publication. Additional mineral analysis has confirmed temperatures inconsistent with normal landslides. The debris field pattern matches simulations of a low-angle airburst better than it matches natural slope failure. And the dating, though imprecise, consistently points to the early Bronze Age, right around 3100 BCE. The climate data has also become more refined. New ice core analyses from Greenland show a distinct cooling event with increased atmospheric particulates around 3100 BCE. Lake sediment cores from across Europe show ash layers dating to the same narrow window. Tree ring data shows evidence of a stress year matching this time frame. Taken individually, each piece of evidence can be questioned or explained away. But taken together, they form what scientists call consilience, independent lines of evidence that converge on the same conclusion. It's not proof, but it's compelling. But what if it wasn't an impact at all? What if we're looking at a volcanic event that's being misinterpreted as something from space? This is the volcano hypothesis, and it has serious proponents. The Mediterranean region is volcanically active and has a long history of major eruptions. The most famous, Santorini, would later devastate the Minoan civilization around 1600 BCE. Could an earlier, unrecorded eruption explain everything we're seeing? Volcanic eruptions can certainly cause cooling events. The 1815 eruption of Mount Tambora led to 1816 being called the year without a summer. Krakatoa in 1883 produced spectacular sunsets and measurable cooling around the globe. A major eruption in 3123 BCE could explain the climate data, the ash layers, even some of the geochemistry. But there are problems with the volcano hypothesis. First, the ash at Khufuls isn't volcanic in origin. Its chemical composition matches pulverized local rock, not magma products. Second, there's no evidence of a major Mediterranean eruption at this time. Santorini, Vesuvius, Etna, all of the major volcanic centers show no activity around 3100 BCE. And third, volcanoes don't create trajectory paths visible from 800 miles away and trackable by ancient astronomers. Another alternative: what if the Sumerians did observe something in the sky, but it never hit Earth? Could the planisphere be recording a near miss, a bright comet, or a large bolide that burned up entirely in the atmosphere? This is appealing because we know the Sumerians observed comets and recorded them. They even had a specific term, Lumashtar, the long-haired star. A particularly bright comet, visible for weeks, would certainly warrant detailed astronomical recording. The problem is that comets and asteroids have very different observational characteristics. Comets are visible because they're constantly shedding material. The iconic tail develops far from Earth, making them conspicuous, but also making their trajectories less predictable. An object massive enough and solid enough to cause the Kofels event would have appeared quite different. Smaller, harder to spot initially, but with a more predictable path once detected. And this is what the planisphere seems to show. Not a fuzzy-tailed comet, but a discrete object with a calculable trajectory. The precision of the track, the notation of what appears to be angular velocity, the marking of a specific impact region, all of this suggests something more definite than a comet sighting. But let's step away from the scientific debate for a moment and consider the human element. Because regardless of whether the planisphere actually predicted the Kofels impact, someone created this document. A real person, living in the world's first civilization, inscribed these marks on this clay. Creating a clay tablet in ancient Sumer wasn't casual work. The clay had to be precisely prepared. Too wet, and it wouldn't hold fine marks. Too dry, and it would crack. The wedge-shaped stylus required years of training to use properly. And the content had to be important enough to justify the time, material, and eventual archival storage. The planisphere was important enough to be preserved, copied, stored in what would become one of the ancient world's greatest libraries. That tells us something. This wasn't a casual doodle or a practice tablet. This was considered valuable knowledge worth preserving across centuries. So imagine you're that astronomer priest. You've spent decades learning the movements of the heavens. You've memorized the positions of hundreds of stars, tracked the paths of planets, predicted eclipses, and then you see something that doesn't fit. Something that's moving wrong. Something that's getting brighter, closer, faster. You take measurements. You make calculations. And slowly, with growing horror, you realize what the mathematics are telling you. This object is going to hit Earth. And you can calculate, roughly, where. What do you do with that knowledge? You record it, because that's what your civilization does. In the face of uncertainty, chaos, or impending catastrophe, you create a permanent record. You preserve the knowledge. You leave a message for whoever comes after. And that's exactly what this tablet represents, regardless of whether modern scientists can agree on its interpretation. It represents humanity's oldest instinct: to observe, to record, to understand, and to warn. To leave something behind that says, we were here. We saw this. We understood. The fact that this tablet survived 5,000 years, through the fall of Sumer, the rise and fall of Babylon and Assyria, through conquest and fire and flood, to end up in a museum where a planetary scientist could examine it with modern software. That's remarkable. That's humanity's long conversation with itself across the centuries. By late autumn of 3123 BCE, the worst had passed. The ash clouds were finally dissipating, blown away by winter storms. The sun returned, pale and distant, but present. The temperature remained cold, but it stopped dropping. The worst of the dying was over. But the world the Sumerians returned to was fundamentally changed. The population had been devastated. Some estimates suggest a 30 to 40% reduction in inhabited settlements. Entire villages had been abandoned. Trade networks had collapsed. The agricultural surplus that supported Sumerian civilization had vanished. And yet, Sumer survived. This is perhaps the most remarkable part of the story. A civilization experiencing catastrophic climate disruption, crop failure, and massive population loss didn't collapse. It adapted. The following spring, the survivors planted what seeds they had left. The irrigation systems, though damaged and clogged with ash, were repaired. Trade slowly resumed as conditions normalized. And within a generation, Sumer was not just recovering. It was entering its golden age. The period from 3000 to 2800 BCE saw the emergence of the first true city-states, the refinement of cuneiform writing, the development of the world's first legal codes. This was when Sumerian civilization reached its peak of cultural and technological achievement. Some researchers believe the catastrophe actually accelerated development. The crisis forced cooperation, innovation, and centralization. Settlements consolidated around the most successful cities. Agricultural techniques improved to maximize yield from limited resources. Social organization became more complex to manage scarce food supplies. The great ziggurats, those massive stepped pyramids that define Sumerian architecture, most of them date to after this period. As if the civilization emerged from crisis with renewed determination to build something permanent, something that would last, something that would reach toward the heavens that had once threatened them. The Khufu's event, if it happened as described, wasn't the last time Earth was struck by an object from space. It happens regularly. Most are small, meteors that burn up harmlessly in the atmosphere, but some are large enough to matter. In 1908, something exploded over the Tunguska River in Siberia. An airburst roughly 20 kilometers above the ground, releasing energy equivalent to 10 to 15 megatons. It flattened 80 million trees across 830 square miles. If it had occurred over a populated area, the death toll would have been catastrophic. In 2013, a meteor exploded over Chelyabinsk, Russia. This one was much smaller, only about 60 feet in diameter, but it still released energy equivalent to 30 Hiroshima bombs. The shock wave damaged buildings and injured over 1,500 people, mostly from flying glass. And we didn't see it coming. No telescope spotted it. No warning was issued. Today, we track about 25,000 near-Earth objects. We know their orbits, their sizes, their trajectories. We can predict, with reasonable accuracy, which ones pose a threat in the coming decades or centuries. We have the mathematics, the technology, the computational power to see what's coming. But we still miss things. Objects coming from the direction of the sun are especially hard to detect. The glare blinds our telescopes. And there are likely millions of smaller objects, 10 to 50 meters across, that we simply haven't cataloged yet. Any one of them could cause a Tunguska-level event if it hit at the right angle. Which brings us back to the Sumerians. Because if Bond's interpretation is correct, they were doing exactly what we do now. They were watching the sky. They were tracking objects. They were calculating trajectories. They were trying to predict impacts. The methods were different. The precision was lower. But the fundamental impulse was identical. Observe the threat. Calculate the risk. Record the data. Warn others. It's what any rational civilization would do when faced with danger from the sky. The real question isn't whether the Sumerians could have tracked an incoming asteroid. The question is, why wouldn't they? They had the mathematical sophistication. They had the observational discipline. They had centuries of accumulated star catalogs and pattern recognition. And they certainly had the motivation, survival. So where does that leave us? With a 5,000-year-old clay tablet that either represents one of humanity's most impressive scientific achievements, or an astronomical coincidence so unlikely that it strains credulity. The planisphere has been examined with every tool modern science can bring to bear. High-resolution imaging, 3D scanning, chemical analysis, astronomical simulation. And the more we look, the more intriguing it becomes, but also more ambiguous. Some researchers remain convinced that Bond's interpretation is essentially correct, that this is a record of asteroid observation and impact prediction. Others believe it's an astronomical document, but recording something else entirely. And still others maintain it's not astronomical at all, but administrative, religious, or mathematical. Part of the problem is context. The planisphere wasn't found in its original location. It was recovered from the library at Nineveh, where it had been copied and stored hundreds of years after its creation. The original Sumerian context is lost. We don't know what other tablets might have accompanied it, what explanatory texts might have existed, how it fit into the broader astronomical record, and much of ancient Sumer remains unexcavated. Political instability, looting, and lack of funding mean that most Sumerian sites have never been properly surveyed, let alone excavated. How many other tablets like this might be buried in the ruins of Ur, Uruk, or Lagash? How many were destroyed before they could be recovered? The same is true for Kofels. The site has been studied, but not exhaustively. A comprehensive impact survey, using modern detection methods, might reveal evidence that earlier researchers missed. Or it might definitively rule out an impact, resolving the geological debate once and for all. And the climate data continues to improve. Every year, we extract new ice cores, analyze new lake sediments, develop more refined dating techniques. The timeline around 3100 BCE is coming into sharper focus. We may soon know, with much greater confidence, whether a major atmospheric event occurred at this time. So the mystery persists. We have intriguing evidence, but not conclusive proof. We have compelling correlations, but not definitive causation. We have a story that fits the data, but other stories might fit equally well. And that's what keeps researchers engaged, because this isn't just about an ancient civilization or an impact event. It's about understanding what's possible, about recognizing that the people who came before us weren't primitives making lucky guesses. They were humans, as intelligent, as curious, as determined to understand their world as we are. Today, over 8 billion people live on Earth, most of them in cities, clustered in coastal regions, dependent on complex global systems for food, water, energy, and communication. We've built the most advanced civilization in human history. And like the Sumerians, we're vulnerable. We know that large impacts are rare. An event like Kofels might happen once every few thousand years. Something truly catastrophic, large enough to threaten civilization itself, might happen once every 100,000 years or more. The odds of it happening in our lifetime are vanishingly small. But smaller events happen all the time. Several times per year, objects large enough to cause significant regional damage pass between Earth and the Moon. We just don't usually notice because space is big and Earth is small, and most of the time, they miss. Which is why we watch. NASA's Planetary Defense Coordination Office tracks near-Earth objects, assesses risks, and coordinates response plans. The European Space Agency runs similar programs. China, Russia, Japan, all the major space powers now have some form of asteroid monitoring, and we're not just watching. In 2022, NASA's DART mission successfully altered the trajectory of an asteroid by ramming it with a spacecraft. It was a test. The asteroid posed no threat, but it proved that we have the technology to deflect an incoming object if we spot it early enough. We also have warning systems the Sumerians couldn't imagine. If an impact was imminent, we could alert the entire planet in seconds. Emergency services could be mobilized. Evacuation orders could be issued. The time between detection and impact could be used to save lives. But here's what the planisphere reminds us. All of this, the watching, the warning, the preparation, it's not new. It's not a modern innovation. It's something humans have always done. We've always looked up. We've always tried to see what's coming. We've always tried to leave warnings for those who come after. The Sumerians weren't alone in watching the sky. Every ancient civilization that left records also left evidence of astronomical observation. Stonehenge aligned with solar and lunar cycles. The Maya predicted eclipses centuries in advance. The ancient Egyptians oriented their pyramids with stunning precision to true north. It goes back even further. Some of the oldest cave art in the world, paintings from 40,000 years ago, includes what appear to be star maps and records of astronomical events. Our ancestors were watching the sky before they built cities, before they invented writing, perhaps before they even had language as we understand it. Why? Because the sky was the first thing that demanded explanation. The sun that brought warmth and light. The moon that waxed and waned. The stars that wheeled overhead in their endless dance. And occasionally, the unexpected. Comets, meteors, eclipses, the things that didn't follow the patterns. And so we watched. We remembered. We passed the knowledge from generation to generation. We built on what came before, adding our observations to the accumulated wisdom of centuries. This is how human knowledge grows, not through sudden inspiration, but through patient observation and careful record-keeping across lifetimes. The planisphere, whatever it ultimately represents, is part of that legacy. A 5,000-year-old data point in humanity's long relationship with the cosmos. It's a reminder that the people who inscribed this tablet were fundamentally like us. They looked up. They wondered. They tried to understand. And they left a record so that we might understand too. So did the Sumerians really predict the Kofels impact? Did they watch an asteroid approach for weeks or months, calculate its trajectory, and recorded in clay for posterity? Or are we seeing patterns that aren't there, connecting events that were never truly connected? The honest answer is, we don't know. We may never know with absolute certainty. The evidence is intriguing but ambiguous. The timeline aligns but doesn't prove causation. The mathematics are compelling but open to interpretation. But perhaps the certainty isn't the point. Perhaps the value of the planisphere isn't in what it proves, but in what it represents. It represents human curiosity, human ingenuity, human determination to understand the universe, even in the face of our own fragility. It reminds us that science isn't new. Observation and calculation and the preservation of knowledge, these aren't modern inventions. They're deeply human practices that reach back to the very beginning of civilization, maybe further. And it reminds us that we're part of a continuum. The same sky that the Sumerian astronomer priests watched 5,000 years ago is the sky we see tonight. The same laws of physics that govern the trajectory of whatever approached Earth in 3123 BCE govern our modern spacecraft. The same human curiosity that drove ancient observers to spend their nights on ziggurat steps drives modern astronomers to spend theirs at telescope arrays. We're all part of the same conversation, asking the same fundamental questions. What's out there? What's coming? How can we understand it? How can we prepare? How can we survive? And when we do find answers, when we do understand something new about the universe or our place in it, we do what the Sumerians did. We record it. We preserve it. We pass it on. We leave a message for whoever comes after, hoping they'll understand what we saw, what we learned, what we tried to tell them. Because that's what humans do. We watch the sky. We see the signs. We try to understand. And we leave a record that says, "We were here. We looked up. We saw something remarkable. And we wanted you to know."